The question that I have is, could you discuss the stress strain and strength behavior of overconsolidated clay during triaxial CU testing? Alright, it's time to talk about the behavior of overconsolidated clays. What I have here are typical results from 3 different tests, not all of which are overconsolidated. In fact, the specimen used in test number 1 is normally consolidated. So just like we did before, I consolidated it up to this point along the virgin compression line and then sheared it under undrained conditions. So this is a typical effective stress path that you will get for a normally consolidated clay, right? So this will serve as a reference test for us to establish the pattern here. So just to remind us, we have a hardening type of curve in the Q epsilon 1 space, and in the E P prime space, the path goes to the left and fails. The failure point lies on the critical state line, right? So this black line over here is the critical state line in the PQ space, and this red line over here is the critical state line in the EP prime space. So these are the same as the one that we talked about in the earlier slides. So within this framework, we're going to try and see how the behavior of overconsolidated clays will plot. Alright, test number 2. First I normally consolidated it along the virgin compression line up to this consolidation pressure, initial confining pressure, then allowed it to swell, okay, up to this point, alright, and then sheared it from that point. So the initial confining pressure for test number 2 is P02 prime, but it's no longer a normally consolidated soil. It's been unloaded to this point, and therefore it is an overconsolidated soil. The overconsolidation ratio is this past consolidation pressure or pre-consolidation pressure PP prime divided by P02 prime. So I marked that over here. It turns out that the effective stress path in the PQ space is approximately vertically up. It just goes vertically up and fails on the same critical state line that this normally consolidated soil had failed. Alright, and in the Q epsilon 1 space, we still have a hardening type of soil, okay, and this point right here doesn't go anywhere because it's already on the critical state line and it stays on the critical state line. So it turns out that as long as the initial point lies to the right side of this critical state line, that is anywhere in this region right here, okay, the behavior is kind of similar, not identical but kind of similar. What do I mean by that? Well, in the PQ space, your effective stress path still leans to the left, okay, and it goes up and fails in the same critical state line, and in here you still get a hardening type of stress strain curve. There's no strain softening. I don't want to crowd my picture too much, but if I were to plot one more, it'll look something like this. It'll lean to the left in the PQ space, fail on the same critical state line, alright, and in the EP prime space, this path will still move towards the critical state line. The failure point will still lie on the critical state line, and in the Q epsilon 1 space, you have a nice hardening type of smooth curve. When the initial point lies to the right of the critical state line, that is between the virgin compression line and the critical state line, we would call such soils as lightly overconsolidated. So the behavior of lightly overconsolidated soil is pretty similar to each other. The pattern changes as soon as the initial point moves to the left side of the critical state line. So that's what happened to test number 3. Okay, so in test number 3, I consolidated it up to PP prime, and then I allowed it to unload it up to this point and then sheared it from that point under undrained condition. Now in the EP prime space, the path moves to the right this time because the critical state line happens to be to the right of this point, right? So the stress path the path always moves towards the critical state line in this space, and therefore it is going this way, and at failure that is at critical state failure, it lies on the critical state line. And this is what happens in the PQ space. Couple of important things to note here. Number one, initially it leans slightly to the right. Number two, it goes through a peak and then falls back to the critical state line that we established earlier. Number three, which is very important, this part of the curve is above the critical state line. Peak point is actually lies above the critical state line we established for normally consolidated clays. And this behavior translates into this behavior in the Q epsilon 1 space. Now we are seeing strain softening behavior. So there's a peak, there's an ultimate. So in terms of failure, two important points to note here. Number one, regardless of the overconsolidation ratio, eventually, right, all of these specimens fail on the same critical state line. In other words, the ultimate failure happens on this critical state line. On the other hand, as soon as the soil becomes heavily overconsolidated, this is what we would call heavily overconsolidated, then the peak is different from the ultimate. Now you can define two different failure states, right? Ultimate failure state, peak failure state. So this starts to happen from this point on, right? From the point where the unloading curve crosses the critical state line all the way in this region. So if I were to take all these peak points, connect them by approximately a straight line, my straight line is going to look like this. So this is what people call failure line, but of course here exactly what that means is we are connecting all the peak points. Alright, so if I did another test in between, right, it would have gone up like this and the peak point would lie approximately on this failure line right there. Here I have summarized some of these observations. So what about the shear strength parameters? Well, here are the Mohs circles corresponding to the three tests. Since the specimens used in test 1 and 2, that is this one and this one, fail on the critical state line that passes through 0 here on the PQ space, the line tangent to these two circles must also pass through 0 in the Mohs Coulomb space. So we get one set of shear strength parameters like that. C prime is 0 and phi prime is the friction angle of the soil. These we call the shear strength parameters in the normally consolidated range. Now coming back to the PQ space, we have a failure line based on the peak stresses, right? And that failure line went from this blue line to this green line right there, right? So I take the blue circle here and the green circle here and then define a failure line based on that, based on them. Now that failure line has an intercept now in the Mohs Coulomb space, just like this PQ failure line has an intercept on the Q axis. So these we call the shear strength parameters in the overconsolidated range. So now you can see the shear strength parameters depends on the degree of overconsolidation. If it's a normally consolidated, we have one set. If it's an overconsolidated soil, we have another set. But that set now depends on the degree of overconsolidation ratio. One more point I want to make here is that this blue circle right here, right, has a overconsolidation ratio of not exactly 1. Let's just assume that the overconsolidation ratio of that soil is 1.5 because we know we have allowed it to rebound up to this point, right? So it is lightly overconsolidated but not necessarily a normally consolidated soil. But in practice it's kind of difficult to find exactly that point, and therefore this is the assumption we make from a practical point of view. In other words, we start this line from the circle that corresponds to a normally consolidated specimen. So the bottom line is that the normally consolidated soils do not exhibit cohesion on a Mohs Coulomb failure criterion sense. Of course, we have discussed this in detail in an earlier video, right? But an overconsolidated clay or a cohesive soil for that matter does exhibit cohesion. An important point has to do with the variable controlling the cohesion of overconsolidated clays. So I have this graphic here to explain that. Say I did one set of tests with this pre-consolidation pressure, P1 prime, and I got this failure line based on the peak failure stresses. I carried out another set of tests using this pre-consolidation pressure, P2 prime. Alright, so that means you consolidate it up to that point and then allow it to swell to various points and repeat triaxial test, right? And say I got this failure line, again based on the peak failure stresses. So you see, I got different intercepts in the PQ space. So what that translates into in the Mo Coulomb space is that I end up with a different cohesion. And I got COC1 based on the first set of tests, all of which had a pre-consolidation pressure of PP1 prime, and I got COC2 based on the second series of tests, all of which had the same pre-consolidation pressure of PP2 prime. But the PP2 prime is greater than PP1 prime, and therefore I get a higher cohesion. So the bottom line is cohesion of overconsolidated soil is actually a function of the pre-consolidation pressure.